Okay, so we are recording here. Can everybody see the page there for section 1.3 vector equations? It's showing up okay in the viewer. Maybe give me
Yes,
a
I can
thumbs
see
up.
it.
Wonderful, wonderful. Okay, so vectors, of course, in physics and engineering. Thank you, thank you. Vectors in physics and engineering represent forces. And you have components of forces. Okay, so in linear algebra, the way we denote a vector is, so first of all, if the letter is in bold, that represents a vector. Okay, and we use matrices to denote the components. We use matrix notation to show the components of vectors. So two-dimensional vectors are going to have two components, and you can think of the components also as ordered pairs. So if we, for vectors in R2 or two-dimensional space. So the operations that are done on vectors, we can add vectors, we can subtract vectors. Okay, I mean, we can take a vector and multiply it by a scalar. So in example 1 here, okay, they give us vectors u and v, and they want you to find the vector 4 times u, the vector -3 times v, and then the vector 4u plus -3 times v. And they show you below in the solution how to do that. I mean, I hope it's pretty intuitive what they're doing. You know, the way you add two vectors is you add their corresponding components. If you multiply a vector by a scalar, the scalar multiplies each of the components. So, I mean, are there any questions on the solution there that you see in example 1 from the book? All right, if you're good with that, they comment here, they make rather an important comment here, that sometimes to save space, the text may write a column vector like 3, -1 in the coordinate form. Okay, and in this case, the parentheses and the comma distinguish the vector 3, -1 from the 1 by 2 row matrix 3 there. So in other words, like below, they say that the column vector that has 3 and -1 is not equal to the row vector with 3, -1. But the column vector with 3, -1 would equal the vector with coordinates 3 and -1. That's all they're trying to say. And it's just notation. And they talk about geometric descriptions here of R squared. And there they have some coordinates, and they've drawn some vectors to the coordinates. So remember, a vector, I think most of you probably have seen them before, but vectors have direction and magnitude, direction and length. Okay, so they've drawn 3 vectors there in the picture in figure, well, that's figure 2 actually. So, I mean, are we okay with, they in figure 1, they have vectors as points, and in figure 2, they have vectors with arrows in them. So are there any questions on that?
Can you go over what the difference between a column vector and row vector are again?
A column vector would be, I'll show you that on the whiteboard actually. hold on. A column vector, like for instance, 3, -2, 1. That's a column vector. This is a column vector. If you had the numbers 3, -2, 1 like this, they call that a row vector. Row means horizontal, going across. Column means vertical, going down. That's all. That's all they're talking about there. And okay, very good. The book, of course, see, like in courses like multivariable calculus, well, you'll deal with two-dimensional vectors and then three-dimensional vectors as well, vectors in R3. Okay, if you have vectors in R3, okay, then you have 3 entries in the column vector. But in linear algebra, we can go further. We go further. We can talk about vectors in Rn. We can talk about vectors in n-dimensional space. And those column vectors would have n components. So you see, in linear algebra, we go beyond 3 dimensions. All the material you're learning is applicable to n-dimensional space. And of course, there are properties of vectors, algebraic properties, that should be, you know, like the first property there, u plus v equals v plus u. That means vector addition is commutative. And the second property there, where they have u plus v in parentheses plus w equals u plus v plus w in parentheses, that means vector addition is associative. And you know, there are all these properties that when you do problems, it's going to be pretty straightforward, I think. I'm not too worried about that. What I do want to talk about here in a little more detail is this example here. So let me give you an example for your notes. I want to talk about something called a span. A span. So let me give you a moment to copy that down. All right, take your time. All right, so for this problem, you're being given vectors A1 and A2. Okay. And, well, hold on. Let's get that file. Yeah, you know, A1 is an element of our two-dimensional space, and so is A2, so is that vector. That lies in two-dimensional space. And so does the vector B. And we want to know if B is in the span of the two vectors A1 and A2. So think of a span as like what does to span mean in general terms, like sort of in everyday terms? Like a bridge spans, right, over a river. What does span mean? Sort of, what's a synonym for span? If something spans, there's kind of a word I'm looking for. Covers, yeah, that's right. Covers a width. That, all right, Mikhail. And there's a word I'm looking for too. Encompasses. Hold on. It's a 7-letter word. REAC. A span reaches. That's right, Marcella. That's so a span, you know, the span reaches over the river. The bridge spans over the river, it reaches over the river. So we want to know if the set of vectors A1, A2, if that set of vectors, in a sense, if the vector B can be reached by a linear combination of A1 and A2. That's what there you go, Mikhail, wingspan. There you go. So let's see how this works. First of all, we need to have criteria here. So to see if a vector B is in the span of a collection of vectors A1 and A2, we need to see if the vector B can be written as a linear combination of A1 and A2. That's how you tell if a vector B is in the span of vectors of the set of vectors A1 and A2. Can the vector B be a linear combination of A1 and A2? Is the vector B reachable with using the vectors A1 and A2? Okay, let me give you a moment to copy. And that's right, Bellen, you're correct on that. Well, yeah, I don't know, but okay. Relate what you want to it. That's fine. But look, how do we take this definition that B is in the span of the set of vectors A1 and A2? Okay, if B is a linear combination of A1 and A2, the way if B is a linear combination of A2, that means x1, some scalar x1 times the vector A, plus some scalar x2, I'm sorry, some scalar x1 times the vector A1, plus some scalar x2 times the vector A2 will equal the vector B. Okay, that means if there were an x1 and an x2, if there were scalars that exist, in other words, if a solution x1, x2 exists, then B can be written as a linear combination of A1 and A2. And by the way, this here is what's called a vector equation. It's an equation that has vectors in it. Okay, a differential equation has an equation with derivatives in it, right? Well, a vector equation is an equation that has vectors in it. And we want to see if the vector B is in the span of the set of vectors A1 and A2, we need to see if this vector equation can be solved. And so what we're going to do is we're going to multiply through the scalars x1 and x2, as you see was done on the next step. And then on the left-hand side, we can add those two vectors, right? We can add those two column vectors, as you see in the next step. Are there any questions up? Are there any questions up to here? Okay, well, if you're good with that, what we want to do now is, you know, we're trying to find x1 and x2 such that these two vectors are equal. Well, if they were equal, that means x1 plus x2 would have to equal 2, and x1 minus x2 would have to equal 4. So, oh, we're back to solving systems of equations again. So the vector equation is giving us a system of equations. And now we're going to solve that. And I saw that some people already offered some answers here. That's okay. So let's go ahead and we'll write down the augmented matrix here. And this is optional, the dashes. And we're going to do row operations. And we're going to get this matrix in reduced echelon form. To see if we can solve for x1 and x2. May I go to the next page? Is everybody good so far? All right. Cameron's good. Maybe I'll get a few more thumbs up. I just want to kind of make sure that, all right, David and Marcella, wonderful. Okay. So, and Belen, wonderful. Okay, let's solve the system. Okay, well, we're used to writing the system as an augmented matrix, and we'll do row operations here. Okay, that's easy enough. So let me see here. Hold on, clear that. Boom. Blow that up a little bit. Okay, so here we took -1 times the first row and added it to the second row. And put the result in the second row. Okay. All right, so that was in terms of well, yeah, okay. And of course, we use the 1 as a pivot. Now, we have a -2 here as the leading entry. We'd like it to be a +1. So we did get a +1 here. And so we took -1/2 times the second row and put the result in the second row. Now we're going to use 1 as a pivot to produce a 0 where this 1 is above it. And so what we do is here we took -1 times the second row, added it to the first row, and put the result in the first row. It's a -1/2, of course, but let me just. So this gets us then where we need to be in terms of just one moment here. Yeah, now it turns out that x1 is 3 and x2 is -1, right, based on our augmented matrix. And so that means then, that 3 times a1 plus -1 times a2 equals the vector b. And I drew a picture here where I drew the vector b. The vector b is at 2, 4, right? The vector a1 was at 1, 1, and the vector a2 is at 1, -1. Okay. And indeed, if you take that vector a1 and you multiply it by 3, that's going to get you here. And if you take the vector a2, which is this vector here, and you multiply it by -1, that's going to give you this vector here. And so 3a1 and plus -a2, and you know how to add vectors, you add them tip to tail, right? So that does give you 2, -4. And therefore, the vector b is in the span. It is in the span of a1 and a2. It is. The vector b was reachable using a linear combination of a1 and a2. Mikhail, would all integer, it turns out because, yes, because the vectors a1 and a2, and you can see that in the diagram, and notice I got out my trusty ruler so I could draw a nice picture there. The vectors a1 and a2 in the diagram here are what are called linearly independent. They're not multiples of each other in this case. They're linearly independent. And so you could take any vector in two-dimensional space and write it as some linear combination of those two linearly independent vectors, a1 and a2. Now, you know, linear independence is a topic that we're going to be getting into when we get to section 1.7. Very important. But sure, the vectors A1 and A2, I want to say this the right way. How could I say this? I want to be careful not to, say more than I need to, but basically, we can say that, I mean, if we wanted to be, we could say that the span of A1 and A2 is equal to R2. Because any linear combination of the vectors A1 and A2 would give you a vector in R2, and any vector in R2 can be written as a linear combination of those two vectors. So, all right, are there any questions on that? Okay, let me show you just an example here from the book. A few things from the book that are important. In terms of notation. So we can denote a vector equation. You see in the top box there, you have this vector equation, but you could denote the vector equation as a matrix where the columns are the A1, A2 up to AN and vector B. It's just two different ways. The vector equation can be expressed, I want to say this the right way. The vector equation has the same solution set as a linear system with that augmented matrix. I mean, we basically just did this, right, with the example that we did. We took a vector equation and expressed that vector equation. I want to say this the right way. We took a vector equation and rewrote the vector equation as an augmented matrix. That's what we did. And there are going to be times where, let me just see if I can find this. There was an example I wanted to, oh yeah, here, this is important. This is about a geometric description of the span of a vector V and a span of a vector, two vectors U and V. So you see there in figure, this is figure 10. Hold on. It's always helpful to have geometric feel for linear algebra. So in figure 10 there, you see they have a vector V in three-dimensional space, and the span of that vector V geometrically would just create a line in three-dimensional space, because the span of the vector V is any multiple of the vector V. And so that would trace out a line in three-dimensional space. Now in figure 11, you have the span of two vectors in three-dimensional space. The span of two vectors in three-dimensional space is any linear combination of those two vectors. And that would have to trace out a plane in three-dimensional space. That's the span of, that's what a span of two vectors would be. Are there any questions on these two figures, figures 10 and 11? Who's feeling good with those figures and the geometry? Maybe give me a thumbs up if you're okay with them. Jonathan is, Mikhail is, wonderful. Okay, Jacob, wonderful. Thumbs up on that. All right, well, let's look at one more example here then. One moment. Yeah, all right, let's see here. So let's look at example 6. So example 6 says, all right, you have vectors A1 and A2 in 3-dimensional space and a vector B also in 3-dimensional space. Okay, so maybe, hold on here. Try to highlight things a little bit here. And the span of those two linearly independent vectors, A1 and A2, would have to be a plane through the origin. And we want to know if the vector B is in that plane. That's the same as saying, is the vector B in the span of A1 and A2? So again, we have to then say, does this vector equation have a solution? All right, well, we're going to write down, as you see below, the augmented matrix for that vector equation. You see it there. And they do row operations. And the third equation is 0x1 plus 0x2 equals -2, which has no solution. This means that the vector B is not in the span of A1 and A2. So that's an example where you see we're looking at different concepts in linear algebra, but ultimately then to answer the types of questions, we ultimately end up with a system of equations that we need to solve. Because a vector equation ultimately becomes a system of equations that we need to try to solve. And if it's consistent, then the vector is in the span. If it's inconsistent, the system, then the vector is not in the span. Okay, so really this is really what section 1.3 is about. And I think you have enough information here now. I think we've covered it well, and you should be able to work on the section 1.3 homework as well. When you do these problems now, continue doing the row operations and work them out by hand. The problems are not that large. You know, for your first exam, which is going to be posted on Monday, February 7th, you know I'm going to want you to, after you complete the exam, I'm going to want you to upload your work. And I want to see, I want you to work problems out by hand and so because I need to see that you can do row operations and understand the concepts. So show your work, do your homework just like you would do the exam, of course. Okay, so that you're well prepared, and it'll help you understand the concepts too. Mikhail, we will be doing section 1.4 on Monday. Yes, we will be doing 1.4 next time on Monday. Absolutely. Are there any? Okay, very good. Cameron, the questions on the exam will be similar to homework questions. If you can do your homework questions well, you ought to be able to do exam questions well. And could you see something on the exam could you see a questions that you haven't exactly seen before? You could, but it ought to be something you can manage if you understand the homework well. Okay, you're welcome. And David, I actually would appreciate if when you do your work that you write out the row operation on the right side, like are you doing -2 times row 1 plus row 2 and replacing the result in row 2. It's helpful for me to see that in your work. Now, once you get more experienced, you won't need to do that. But for the first test and for your work now, please go ahead and put in the row operation instructions. It only takes a second to do, right? And let's see, Mikhail says, can we do more than one row operation per displayed step? Sure, if you do like 2 row operations and then get the matrix to another matrix, and you did 2 row operations at once, that's okay. That's okay. If I can follow it, that's fine. Excellent questions. Are there any other good questions before I stop the recording here? You're welcome. Okay, I'll stop the recording.